Every day, glass is made by turning ordinary sand into a clear, solid sheet. In a hot furnace, silica grains melt, bubble, and unify into a glowing river. This episode follows flat glass, the window and mirror material that shapes cities and cars. You will see the float process, where molten glass rides on liquid tin and levels itself smooth. Rollers guide the edges, line speed sets the thickness, and the surface comes out polished by physics. Next comes the annealing layer, a long tunnel that cools the sheet gently and locks in strength. Cameras and sensors watch for waves, stones, and bubbles, while rejected glass is crushed and reused. We will end in a small studio where artisans mix colors, roll slabs by hand, and cut them to size. If you enjoy real processes, follow the channel and stay to the end for the final review. Our story starts far from the furnace, at silica-rich deposits where pale sand is dug like a harvest, scooped by loaders and carried in steady convoys. The goal is not just volume, it is purity, because tiny traces of clay, iron, or organic debris can tint the final sheet or create defects. At the processing site, the sand is washed with rushing water, shaken through vibrating screens, and separated so only uniform grains continue forward. Magnets and density separators help pull out unwanted minerals, while settling tanks calm the slurry and return clean water back into the loop. When the sand dries, it looks like simple powder, but it is mostly quartz, the silica backbone that will become glass once the heat is high enough. From here, bulk trucks deliver thousands of tons to glass plants, where towering silos store sand, soda ash, limestone, and recycled glass pieces called cullet. Each ingredient has a job, and the recipe is measured carefully because flat glass demands consistency, day and night, sheet after sheet. Silica provides the structure, soda ash lowers the working temperature, and limestone stabilizes the network, so the glass resists moisture and chemical attack. Cullet is the quiet efficiency boost, because it softens sooner than raw minerals, cutting fuel demand, and helping the melt become more uniform. Operators blend these dry materials into a batch, a pale mixture that pours like grain and flows by conveyors into the feeding system. Before anything melts, quality checks confirm grain size, moisture, and contaminant levels, so the furnace does not inherit problems it cannot fix later. The batch then enters the melting end of a continuous furnace, a massive chamber lined with refractory bricks that can run non-stop for years. Burners fire overhead, often with natural gas, raising the interior toward the intense temperatures needed to fuse minerals into a glowing liquid. As heat climbs, carbonates release gas, the mixture foams and clears, and the melt slowly changes from cloudy to transparent, like dawn forming through fog. Inside the hot zone, convection currents stir the liquid glass, smoothing out composition and helping bubbles rise so they can be removed in later stages. This is where modern flat glass begins to separate from older methods, because the melt is prepared for a continuous sheet, not a single pour onto a table. Every second matters, with sensors tracking temperature and flow, while feeders keep the batch steady, so the glass river never starves or surges. When the melt is clean, calm, and evenly viscous, it is ready to leave the furnace and glide toward the float bath where perfect flatness is born. The liquid glass leaves the furnace at a blinding heat and flows through refining zones where the temperature is carefully shaped to drive out remaining bubbles. In these chambers, the melt is held hot enough to let gases escape, while its surface calms and the composition becomes uniform from edge to edge. Then the glass river reaches the float section, a sealed corridor that feels like a quiet laboratory built for fire. Inside, a bath of molten tin waits below, protected by an atmosphere of nitrogen and hydrogen, so the tin surface stays clean and does not oxidize. Because tin is far denser than glass, the molten glass naturally spreads across it, floating like oil on water and forming a continuous ribbon. Surface tension pulls the ribbon smooth, gravity levels it, and the tin provides a mirror-like base that leaves the underside perfectly polished. At the entry, the glass is extremely hot, and it behaves like thick honey, slowly relaxing into a flat sheet as it advances forward. Along the sides, rollers guide the edges, and the line speed becomes a powerful dial that sets thickness, from thin panes to heavier plates. As the ribbon travels, it cools gradually, becoming stiffer, while its top surface is also smoothed by fire polishing and controlled heat. The soundscape is a steady industrial hush, burners breathing, motors humming, and the faint metallic whisper of rollers touching the glowing edges. By the time the sheet approaches the end of the tin bath, it is already a solid form, but it still holds internal stress from the heat it has survived. That is why it enters the annealing layer, a long tunnel where the temperature drops in slow, planned steps instead of a sudden shock. Inside the layer, the glass relaxes, microscopic tensions unwind, and the sheet becomes stable enough to cut without cracking like ice. At the exit, the ribbon is now near room temperature, moving fast on conveyor rollers and shining with the flatness that float glass is famous for. Automated scanners inspect the surface for ripples, stones, scratches, and tiny trapped bubbles that could weaken the pane or distort reflections. If defects appear, operators can adjust heat, speed, and chemistry, because this line runs continuously, and every correction must happen in real time. When quality is approved, diamond wheels score the sheet. The glass snaps cleanly along the line, and the edges are trimmed to precise dimensions. Any rejected pieces are crushed into cullet and returned to the batch, closing the loop so the factory wastes less energy and less raw material. After cutting, the finished sheets are lifted and stacked upright on metal racks, separated by protective pads, so the surfaces do not scratch in transit. Forklifts move these towering bundles through wide aisles, where labels track size, thickness, destination, and the production conditions that created them. From here, flat glass can be shipped as it is, or sent to other lines where it becomes tempered, laminated, coated, or mirrored for specific uses. Even without extra treatments, the float process has already delivered what builders need most: a pane that is flat, clear, and consistent across huge areas. In a control room, engineers watch a wall of screens that report furnace temperature, tin bath conditions, Lehr curves, and optical quality in one live dashboard. A small change in burner output, batch feed, or line speed can shift the entire sheet, so the operators learn to read the line like farmers read weather. This constant monitoring is why modern flat glass feels so uniform, because the process is not a single event, it is a continuous balance. Now, the scene changes. From an endless ribbon of glass to a workshop where time moves by hand, and every sheet has a personal signature. In an artisanal furnace, different compartments hold molten glass in different colors, glowing like separate pools of sunset. The team works fast because glass cools the moment it leaves the heat, and slowing down can freeze a piece before it becomes a clean panel. With long ladles, they gather a portion of liquid glass and carry it to a mixing table while keeping it in motion to prevent premature stiffening. To create marbled patterns, they combine several colors, folding the incandescent mass together until streaks and swirls appear like paint in water. A special fork-like tool stirs the surface, blending tones without losing the dramatic lines that make handmade glass so alive. Next, the glowing mass is guided into a roller machine where heavy cylinders press it flat, and the gap between the rollers defines the final thickness. You can hear the soft crackle of heat, the low rumble of the rollers, and the quick taps of tools as artisans correct edges before the sheet cools. Once the shape is set, the sheet goes into an annealing kiln, where the temperature falls slowly, protecting it from stress fractures and hidden cracks. When it is stable, the panel can be cut, sometimes by hand with a diamond or tungsten carbide cutter, scored carefully, then snapped with practiced control. Industrial lines chase perfect repetition, while artisans chase character, but both rely on the same truth: controlled heat turns sand into a lasting surface. From washed silica sand to a glowing batch, the journey begins with purity, precision, and a furnace that never sleeps. Inside that heat, minerals fuse into a clear melt, refined until bubbles fade, and the glass becomes calm and uniform. The float bath then performs its quiet magic, as molten glass glides over liquid tin and levels into a smooth ribbon by gravity and surface tension. In the annealing layer, controlled cooling locks the structure in place, so the sheet stays stable when it is scored, snapped, and trimmed to size. Sensors keep watch. Cullet returns to the mix, and the line keeps flowing, turning massive demand into endless panes for homes, cars, and cities. In the workshop, artisans repeat the same thermal discipline, but add color, mixing, and rolling by hand to create panels with personality. Two worlds, one industrial and one handmade, prove that glass is not just fragile, it is engineered through temperature, timing, and care. If you want more full process stories like this, follow the channel, leave a like, and tell me where you are watching from. Thanks for staying to the end, and click one of the next videos on your screen to keep learning with me.